Welcome to the next subject, next session of subject engineering maths, chapter 2 differential equations. We were in the concept of solving first order, first degree differential equations. We have completed 7 methods to solve first order, first degree differential equations. We have 2 more methods to solve them. Now, let us start the session with a definition: linear equation in X. Next one is definition: linear equation in X. Suppose I have an equation like this: dx by dy plus px equal to q into x power n. What about this p and q? P comma q are either constants or functions of y only. So in that case, this is called a linear equation in X, and of course this is basically extension of linear equation in X. Suppose if n equal to 0, then it is called linear equation in X. Suppose if n is not equal to 0, then this equation will be called as Bernoulli's equation in X. This is called Bernoulli's equation in X. Already we have seen this linear equation in X. If I don't have this x power n, see here n is a constant. So I don't have this means n is 0. So when n is 0, this is called linear equation in X. dx by dy plus px equal to q. Now here p comma q are either constants or functions of y, because here y is an independent variable. Here y is nothing but an independent variable. So whenever an equation is in the form dx by dy plus px equal to q into x power n, where n is some constant other than 0, then it is called Bernoulli's equation in X. Right? Now write this definition: Bernoulli's equation in X. Bernoulli's equation in X. An equation of the form dx by dy, an equation of the form dx by dy plus px equal to q into x power n, dx by dy plus px equal to q into x power n is called Bernoulli's equation in X. An equation of the form dx by dy plus px equal to q into x power n is called Bernoulli's equation in X, where p comma q are either constants, or functions of y only, that is independent variable, and n is a constant not equal to 0, Let us have one example. Suppose I have an example dx by dy plus, here p is a function of y, I will take like this. For example, x by y equal to q is a function of y. So for example, I can write cos y into y square. Now in this case, what is my p? P is nothing but 1 by y. What is q? Q is cos y. What is n? Here n equal to 2. Therefore, this is an example of a Bernoulli's equation in X. dx by dy plus px equal to q into y power n. So sorry, this is x power n. So in that case, this is called Bernoulli's equation in X. P is 1 by y, q is cos y, and n equal to 2. Therefore, this is an example of Bernoulli's equation in X. Now let us try to find the general solution of Bernoulli's equation in X. That is method number 8. That is method 8. So this is solving Bernoulli's equation in X. Solving Bernoulli's equation in X. Suppose I have an equation like this: dx by dy plus px equal to q into x power n. We call it as equation 1. In the last session, we have discussed solving Bernoulli's equation in y. What is the general solution of Bernoulli's equation in y? That is y power minus n into if equal to integral qb into 1 minus n into I of dx plus c. This is basically the general solution of Bernoulli's equation in y. This is nothing but general solution of Bernoulli's equation in y. What is this IF? This IF is nothing but e power integral p into 1 minus n dx. Therefore, if I want to get the general solution of Bernoulli's equation in x, interchange the positions of x and y. Therefore, in place of this y, I get x power 1 minus n. In place of this dx, I will get dy. And this if equal to e power integral p into 1 minus n dy. Therefore, this is the general solution of Bernoulli's equation in x. Note this. Yes, we discuss Law's method to solve first order, first degree differential equations. That is total derivative method. Now we discuss method number 9. Solving equations by total derivative method. Let us see what do you mean by a total derivative. Generally, we have three types of derivatives. Generally, what derivative measures? Change in y with respect to some variable. Change of some variable with respect to some variable. Suppose if y depends on only the variable x. If y is a function of x only, then I can discuss dy by dx. If y is a function of x other than some another variables, for example z, then I can discuss dou f by dou y or dou f by dou z. So partial derivatives will be repeated whenever a variable is expressed in terms of more than single variable. Now this is ordinary derivative and these are partial derivatives. Suppose if I do like this dy, for example. Now in this case, what I will get is this dy is nothing but change in y. So therefore here, suppose here I wrote y equal to function of x comma z, or I can do like this. Here y is a function of x comma z, then I can discuss dou y by dou x. Here y is a function of z, I can discuss dou y by dou z. So this is ordinary derivative, change in y with respect to x, when y depends only on x. Here y is a function which is expressed in more than one variable, so I can discuss dou y by dou x and dou y by dou z. Therefore y depends on more than one variable, so I can discuss dou y by dou x and dou y by dou z. Another derivative is dy. I am finding change in y not with respect to any variable, and such derivatives are called total derivatives. Change in y with respect to x, ordinary derivative. That means if y depends only on x, I can discuss ordinary derivative. If y depends more than one variable, then partial derivatives will occur. If I am not finding change in y with respect to any variable, I call it as dv, and this is called a total derivative method. Now let us see how to solve equations by using total derivative method. So before discussing the procedure, let me list out few formulae on total derivative method. The formula 1 is this: derivative of xy. Product rule, this is x into dy plus y dx. Next one, derivative of x square plus y square. So apply plus, therefore derivative of x square is 2x dx. Derivative of y square, this is 2y dy. Now formula number 3, derivative of x by y. Now apply coefficient rule, this is y into dx minus x dy divided by y square. Now concentrate on this equation, y dx minus x dy equal to 0. So in the future I will try to analyze what are the integrating factors of y dx minus x dy equal to 0. In earlier sessions, when we gone through integrating factors, we started with this previous example. It has a multiple number of integrating factors. Those integrating factors are this: 1 by x square, 1 by xy, 1 by y square, and 1 by x square plus y square. So all these are integrating factors of this particular equation. One of the reason is here in the numerator we have y dx minus x dy. It is multiplied with 1 by y square. So you consider this as a differential equation, y dx minus x dy equals 0. It is multiplied with 1 by y square. So therefore 1 by y square is one of the integrating factor of this equation. Because of this rule, derivative of x by y is this. Now I will write the formula: derivative of log of x by y. Assume that this is x. Derivative of log x is 1 by x. So this is 1 by x by y into derivative of x by y. So this is y by x into this is y dx minus x dy divided by y square. Therefore this quantity is y dx minus x dy divided by xy. Here also the numerator part is same. This is y dx minus x dy equals 0. It is multiplied with 1 by xy. That's why 1 by xy is an integrating factor. Already 1 by y square is covered. Now I will calculate total derivative of tan inverse of x by y. Now assume that this is x. Derivative of tan inverse x is 1 by 1 plus x square. So 1 by 1 plus x by y whole square into derivative of x by y. So this is nothing but y square by x square plus y square into derivative of x by y is y dx minus x dy divided by y square. Cancel out this y square and y square. We get y dx minus x dy divided by x square plus y square. Interestingly, even here also we are having y dx minus x dy. Therefore 1 by x square plus y square is again an integrating factor of same equation. Similarly, if I calculate this derivative of y by x, this is nothing but x dy minus y dx divided by x square. Now what is my equation? This y dx minus x dy equals 0. This equation is same as x dy minus y dx equals 0. So that is nothing but x dy minus y dx. So it is multiplied with 1 by x square. Therefore all the things are 1 by x square, 1 by xy, 1 by y square, 1 by x square plus y square. All these are integrating factors of same equation, y dx minus x dy equal to 0. So this is the reason why all the things are integrating factors of same equation. Okay. So note down all these formulae by one. Now let us solve two problems on total derivative method. So first one, solve y dx plus x dy equal to 0. Solve y dx plus x dy equal to 0. Now actually this LHS part is derivative of xy equal to 0. Derivative of total derivative of something is 0 means this something must be constant. So x into y equal to c. Therefore this is the general solution of this equation. Of course this can be handled by using separation of variables. This can be handled by solving homogeneous method, and even this is an exact equation. So therefore variable separable method is possible in this case. Homogeneous it works. Even this is an exact differential equation. Even this can solve, we can solve this by using total derivative method. So therefore from this it is very clear that a particular differential equation can be handled by more than one method. But even if you follow by any one of these methods, final general solution will be x into y equal to c. So this is the general solution of this equation, right? Note this. Second problem, solve y dx minus x dy equal to 0. Y dx minus x dy equal to 0. Now, we know that it has 4 integrating factors. 1 by x square is one of its integrating factor. 1 by x square plus y square is another integrating factor. 1 by xy is one integrating factor. Even 1 by y square is another integrating factor. So you can use any one of these integrating factors to get the general solution of this. Suppose I am going to use this complicated integrating factor. So let us multiply this equation with this. This becomes 1 by x square plus y square into y dx minus x dy equal to 0. Now this LHS part is, this is nothing but a derivative of tan inverse of x by y equal to 0. So this implies derivative of something is 0 means this must be constant. So tan inverse x by y equal to c. So this implies x by y equal to tan c. Tan c is nothing but again a constant c. So this implies x by y equal to c. This implies y equal to c by x by c. I mean c by x. Therefore this can be written as, sorry, this is x by c only. X by c. This 1 by c is nothing but again constant. So its general solution is y equal to cx. So they represent straight lines passing through origin. They represent straight lines passing through origin. Even you use either 1 by x square or 1 by xy or 1 by y square, final solution will be y equal to cx. Note this. Now with this we have finished all 9 different methods to solve first order first degree equations. Now let us go to classroom workbook to solve questions on maybe method 8 or method 9 if possible. So let us start with question number, this is 30, exactly the question number 31. So here we were discussing classroom workbook, question number 31. Very interesting question. Let us see what it is. This is the solution of, just open classroom workbook, question number 31. The solution of x into y dx plus x dy, y dx plus x dy into cos y by x equal to y into x dy minus y dx into sin y by x equal to, options are given. So you need to find the general solution of this equation. This is cos of y by x, this is sin of y by x. Now it seems to be a complicated first order first degree differential equation. X into y dx plus x dy into cos y by x equal to y into x dy minus y dx into sin of y by x. Now let us try to solve this by using total derivative method so that simplification will be very easy. Now this is nothing but y dx plus x dy into cos y by x equal to, take this variable x to the right side. So it becomes y by x into x dy minus y dx into, this is sin of y by x. So this implies y dx plus x dy into cos y by x. Now what I will do is, you multiply this with x and divide with x. This is plus minus xy into, this is x dy minus y dx divided by x square, because already here x is there, so multiply with x and multiply with x. When you take this to the LHS, it becomes minus sign. So take this quantity on the left hand side, it becomes minus. So multiply with x, divide with x, you will get this into sine y by x equal to 0. Now let us see what is this LHS part. See here what we have is, this is basically derivative of xy. This is nothing but derivative of xy. So derivative of xy into cos y by x plus xy into rest of the quantity is derivative of cos x by y equal to 0. Now I am writing only this xy into, here minus symbol is there. What is the derivative of cos minus sine? What is y by x derivative? X dy minus y dx by x square equal to 0. Therefore this is very clear. This is the derivative of xy into cos y by x plus, I am writing xy as it is. Here I have minus symbol, minus of x dy minus y dx by x square into sine of y by x. That is nothing but derivative of cos x by y. You can easily verify. Derivative of cos is minus sine into y by x derivative is x dy minus y dx divided by this square. Basically this is y by x. So therefore cos y by x derivative is minus sine y by x into y by x derivative x dy minus y dx by x square. Therefore this is in the form derivative of xy into cos y by x plus xy into derivative of this. Therefore this is nothing but derivative of xy into cos y by x equal to 0. This is one variable, this is one variable. It is a product rule. Single variable, single variable. So derivative of something is 0 means this must be constant. So xy into cos y by x equal to constant c. Therefore we got the general solution just by using total derivative method. Only thing is you need to rearrange the terms so that finally it will be reduced to derivative of xy into cos y by x will be equal to 0. Therefore this quantity must be equal to c. This is simply product rule. Now this. Now we move to next concept, higher order differential equations. By this moment we have completely finished the general solutions of all first order and first degree differential equations along with classroom workbook. Now we go to our next concept, that is higher order differential equations. So the next concept is higher order differential equations. Concept, higher order differential equations. Higher order differential equations. Now let us see the general form of higher order differential equation. Suppose I have an equation like this. P naught into dny by dx power n plus P1 into dn minus y by dx power n minus 1 plus P2 into dn minus 2y by dx power n minus 2 plus and so on plus Pny equal to q of x. Suppose assume that the equation is like this. Now, when you look at this equation, the highest order derivative in this case is n. There is no doubt about dependent and independent variables. Here y is a dependent variable. Y is a dependent variable. And x is an independent variable. That is very clear. X is an independent variable. Now, in this case, the highest order derivative is n. Therefore, the order of this equation is n. Suppose I call this equation as 1. We say that this equation is linear. We say that equation 1 is linear if P0, P1, P2 and so on, Pn, Q of x. All these are either constants. All these are either constants or functions of independent variable x only. In that case, this equation is called a nth order linear equation. Earlier we have seen first order linear equations, dy by dx plus py equal to q. So I recall first order linear differential equations. If I have dy by dx plus py equal to q. Now here I have p naught. This is a constant expression. Now this is p1. This is either a constant or function of x. This is either a constant or function of x. You can call it as P2 or you can call it as Q of x also. No issues. So we know that this is a first order linear equation. Forget about whether it is a linear equation in y or something else, but still it is called a linear equation. So here coefficient of dy by dx is 1. Here coefficient of y is p, that I call it as P1. It is either a constant or function of independent variable x. Q is either a constant or function of independent variable x. Therefore, this equation 1 is extension of this equation. This is a first order linear equation. This is a nth order linear equation. So, whenever you want to say that a differential equation is linear, make sure that all coefficients on the derivatives are either constants or functions of independent variable x only. In that case, it is called a nth order linear equation. Now, let us see a few examples. Suppose I have d square y by dx square plus 4 dy by dx plus 3y equal to, for example, sine 2x. Another example is, suppose I have d square y by dx square plus x dy by dx plus 4y equal to, for example, e power 3x. Assume that I have these two equations. Now we can see here P0 is 1, P1 is 4, P2 is 3. Let me point out these constants. This is 1, so this is P0. This is P1, it is a constant. This is P2, it is a constant, and this is a function of x. I call it as Q of x. Therefore, in equation 1, all coefficients on the left hand side are constants. Right side you can have either a constant or function of x. In that case, this is called a second order linear equation with constant coefficients. It is very clear that I am saying that equation has constant coefficients. Before d square y by dx square we have 1. Before dy by dx we have 4. Before y we have 3. That means all coefficients on the left hand side are constants. So the first constant is 1. Next constant some number. Next is some constant. All coefficients on the left hand side are constants, but all things on the right hand side are either constants or functions of x. Therefore, in this case, this equation 1 is a second order linear equation with the constant coefficients. But when you look at this, here the coefficient is 1, it is clear, but here it is a variable coefficient. So it is a second order linear equation, but not constant coefficients, right? So shortly, we discuss linear equations with the constant coefficients. That means handling these equations is very, very simple, right? Even I can give one more example. Suppose if the equation is like this. I'm going to write third example. Suppose the equation is like this: x square into d square y by dx square plus 2x into dy by dx plus 4y equal to, for example, ln of x. Even when you look at this equation, here p naught is a function of independent variable x. P1 is a function of independent variable x. Here P2 is a constant and Q is a function of x. So even this is also a second order linear equation. But here coefficients are not constants, variable coefficients. Still you can handle these equations very easily, because here d square y by dx square, second order derivative power of x is 2. First order derivative power of x is 1. Here there is no derivative, that is power of x is 0. Here there are equal powers of derivatives and equal powers of x. In that case, handling those equations is very simple. But before going to that, if we have solution to equation 1, then handling equation 3 is very simple. I think all the concept is very clear. So when the equation is like this, then it is called a nth order linear equation, because the highest order derivative is n, so it is called nth order equation. We say that it is a linear equation if all coefficients on the LHS as well as RHS are either constants or functions of x only. In that case, it is called a nth order linear equation. Now we have three examples. Now in the first example, all coefficients on the left hand side are constants. So you need not worry about RHS. It can be a constant or function of x. You can have constants also, no issues. But my focus is on equation with constant coefficients. So here it is 1, 4, 3. So it is a second order linear equation with the constant coefficients. Suppose if I write 0 at this moment, it is called a second order homogeneous linear equation with the constant coefficients. Now in this case, it is a second order linear equation. It is a second order linear equation. If I have 0 in place of sine 2x, it is called a second order homogeneous linear equation with the constant coefficients. So once I complete this, I will try to solve linear equations with constant coefficients. Of course, they are homogeneous equations, right? Write these points. An equation of the form P naught into dny by dx power n plus P1 into dn minus y by dx power n minus 1 plus P2 into dn minus 2y by dx power n minus 2 plus and so on plus Pny equal to q of x. You call it as equation 1. An equation of the form this, equation 1 is called a nth order linear equation, if P naught comma P1 and so on Pn. If P naught comma P1 and so on Pn comma q of x or either constants, if P naught comma P1 comma P2 and so on Pn or either constants or functions of x only, Next note, if P naught comma P1 comma P2 and so on comma Pn, if P naught comma P1 comma P2 and so on Pn are constants, P naught, P1, P2 and so on Pn are constants, and q of x is either a constant or a function of x only, then equation 1 is called a nth order linear equation with the constant coefficients. Example. Write this example: d square y by dx square plus 4 dy by dx plus 3y equal to sine 2x. You highlight this. P naught is 1, P1 is 4, P2 is 3 and sine 2x is q of x. Next note, if P naught comma P1 and so on comma Pn, if P naught comma P1 and so on comma Pn are constants and q of x equal to 0 and q of x equal to 0, then equation 1 is called a nth order homogeneous linear equation with the constant coefficients. Is called a nth order homogeneous linear equation with the constant coefficients. Example, you can write the same example, but in place of sin 2x you can take 0. So d square y by dx square plus 4 dy by dx plus 3y equal to 0. After that you write this example and this example. They are simply second order linear equations. That's it. It's a second order linear equation. It's a second order linear equation. Now we discuss higher order linear differential equations with the constant coefficients with the homogeneous, that is RHS is 0. So the concept we need to discuss is solving nth order linear differential equations, nth order homogeneous linear equations with the constant coefficients. Now let us focus on this. Suppose the equation is like this. P naught into d power n plus P1 into d power n minus 1 plus P2 into d power n minus 2 plus and so on plus Pn of y equal to 0. Here I call this equation as 1. So let me explain what is this d. This d is nothing but d by dx, and this is called differential operator with respect to x. This is called differential operator with respect to the variable x. Now previously we wrote a complicated expression, and that equation, this equation are same, except in the previously we have q of x. Now in place of q of x I have taken 0 because it is a homogeneous equation. So in this case, since I am dealing with the constant coefficients, all these are constants, P0, P1, P2 and so on, Pn, all these are constants. So therefore this equation 1 is a nth order, homogeneous linear equation with the constant coefficients. Just in place of d by dx I wrote capital D, and y is taken common in each term. Therefore this equation is called a nth order homogeneous linear equation with the constant coefficients. Now if I want to solve this equation, I consider roots of one equation. So roots of an equation, that is f of d equal to 0. Now what is this f of d? This LHS part I call it as f of d. So therefore this is simply a function in terms of variable d. I call this capital D as d by dx, but I can view it as a variable. Therefore basically this is called auxiliary equation. This is called auxiliary equation of equation 1. If you have any confusion, replace d by some variable. So this is f of m equal to 0. But this part is f of d. The expression which is in the box, that we call it as f of d. Now replace d by some variable m. Therefore this expression becomes p0 into m power n plus p1 into m power n minus 1 plus p2 into m power n minus 2 plus and so on plus Pn equal to 0. Basically this is called auxiliary equation of this, and this equation mathematically we call it as polynomial of degree n. This is called a polynomial of degree n. Now when you solve this equation, we get exactly n roots. So based on the nature of these n roots, you can expect the general solution of this equation. Throughout the differential equations, we have a single task. What it is? Finding general solution. If boundary conditions are supplied, apply those boundary conditions, you will get the constants. Otherwise, single task is finding general solution throughout the differential equations. Whether it is ordinary or partial equation, our ultimate task is solving differential equations. So when you are working with this equation, its auxiliary equation is defined as f of m equal to 0. But what is f of this m? This I call it as f of d. So this d is nothing but d by dx. So in place of capital D, take some new variable m. F of m equal to 0, and that is called an auxiliary equation of equation 1. This is a constant expression. Generally, if you have habit of taking x, you can take x. But why we were not taking x is already we are using variable x for independent variable x. That's why I have taken a variable m. So this is a p naught into m power n plus p1 into m power n minus 1 plus p2 into m power n minus 2 and so on plus pn equals 0, and this is called auxiliary equation of this. Basically, this is a polynomial expression of degree n because it is a nth order equation. When you solve this equation, we get exactly n roots. Sometimes roots can be real, all roots can be complex, few roots can be real, few roots can be complex. So based on the nature of real and complex roots, you can get the general solution of equation 1, right? Hope you understand this. Note these points. Consider an equation p naught into d power n plus p1 into d power n minus 1 plus p2 into d power n minus 2 plus and so on plus pn of y equal to 0, equation 1, where d equal to d by dx, which is called a differential operator with respect to x, Next, the auxiliary equation of equation 1, is given by f of m equal to 0. This implies p naught into m power n plus p1 into m power n minus 1 plus p2 into m power n minus 2 plus and so on plus pn equal to 0. An auxiliary equation of equation 1 is given by f of m equal to 0. Implies this expression is equal to 0, which is a polynomial of degree n, hence it has exactly n roots. Now let us see the general solution of this equation 1 and how to get that general solution. So the general solution of that equation 1 is given by y equal to yc. This is the general solution of equation 1. What is this yc? This yc is called complementary solution of equation 1. This yc is called a complementary solution of equation 1, and this yc depends on roots of the auxiliary equation. The auxiliary equation is f of m equal to 0. So what is the general solution of equation 1? Y equal to yc. Here yc is called a complementary solution of equation 1, and this yc depends on roots of its auxiliary equation 1. Note these points. The general solution of equation 1 is given by y equal to yc. The general solution of equation 1 is given by y equal to yc. Highlight this, where yc is called a complementary solution, which depends on roots of f of m equal to 0. yc is called a complementary solution which depends on roots of f of m equal to 0. Roots of f of m is 0. Now our next task is how to get this yc, right? So next concept, procedure to find yc. Next one is procedure to find yc. Suppose when you start with second order equation, if n equal to 2, that means n represents order of an equation. So if n equal to 2, so the auxiliary equation is f of m equal to 0. So how the auxiliary equation will be? This will be in the form like this. For example, am square plus bm plus c equal to 0. Because here order of the equation is 2, therefore its auxiliary equation is a polynomial of degree 2. This is a polynomial of degree 2. Since it is a polynomial of degree 2, it has exactly 2 roots. We call those roots as m1 comma m2. Now we discuss case 1. Suppose if m1 comma m2 are real and distinct. If the roots are real and distinct, then my yc will be like this. So the value of yc is c1 into e power m1x plus c2 into e power m2x. This is my general solution. See, here we are starting with n equal to 2. Don't think that this procedure is valid. We are finding procedure only for second order equation. The same yc's you can implement for third order equation, fourth order equation, any nth order equation. But as a sample, we were starting with n equal to 2. So when you take n equal to 2, auxiliary equation f of m equal to 0 will be in the form am square plus bm plus c equal to 0. Actually this a is nothing but p naught. This is p1 and this is p2. I write clearly, this a naught is basically p naught. This b is p1 and this is p2 and this is q of x. Now you compare this with equation 1, it will be very simple. Since we are dealing with linear equations with a constant coefficients, p naught is constant a, p1 is constant b, p2 is constant c, right side is 0. So therefore, when you are working with the second order equation, my auxiliary equation will be in the form am square plus bm plus c equal to 0, which is a polynomial of degree 2. When you solve this equation, we get 2 roots m1 comma m2. If both the roots are real and distinct, m1 and m2 are real roots and distinct, then my yc will be like this. c1 into e power m1x plus c2 into e power m2x. Now case 2. Suppose if m1 comma m2 are real and equal. If m1 comma m2 are real and equal, implies yc equal to c1 plus c2x into e power, you can use either m1 or m2 because both are same. So this is my yc. Both the roots are real and equal. Then yc will be like this. So c1 plus c2x. Here multiples of x will come. If I deal with third order equation, if all the 3 roots are real and distinct, real and equal, then I will get c1 plus c2x plus c3x square. Powers of x will be in increasing order along with e power m1x. Now let us deal with case 3, that is roots are complex roots. Suppose if m1 equal to alpha plus I beta, comma m2 equal to alpha minus I beta. So roots are complex roots, then yc equal to e power alpha x. yc equal to e power alpha x into c1 cos beta x plus c2 into sin beta x. So this is my yc. Therefore, when the roots are complex roots, you will get trigonometric functions, cos and sine along with exponential function. So real part is assigned to exponential function, imaginary part is given to trigonometric functions. When you look at all the three cases, every general solution contains two constants C1 and C2. Every general solution contains two constants C1 and C2. Because it's a second order equation, when you handle this, general solution contains two constants. Note all these points. I dictate these points. Consider a second order homogeneous linear equation with the constant coefficients. Consider a second order homogeneous linear equation with the constant coefficients. A second order homogeneous linear equation with the constant coefficients having roots m1 comma m2, having roots m1 comma m2 for its auxiliary equation. Consider a second order homogeneous linear equation having m1 comma m2 as roots of its auxiliary equation. Case 1. If m1 comma m2 are real and distinct, if m1 comma m2 are real and distinct, then yc equal to this: c1 into e power m1x plus c2 into e power m2x. If m1 comma m2 are real and distinct, then yc equal to this. Case 2. If m1 comma m2 are real and equal, if m1 comma m2 are real and equal, then yc equal to this: c1 plus c2x into e power m1x. c1 plus c2x into e power m1x. Next, case 3. If m1 equal to alpha plus I beta, comma m2 equal to alpha minus I beta, then yc equal to e power alpha x into c1 cos beta x plus c2 sin beta x. yc equal to e power alpha x into c1 cos beta x plus c2 sin beta x. Highlight all yc's in case 1, case 2, case 3, right? Where c1 comma c2 are constants. Where c1 comma c2 are constants. Now, when you observe all this, in case 1, if the roots are real and distinct, answer will be constant multiples of exponential functions only. Suppose if the roots are real and equal, then answers will be variable multiples of exponential function. See, suppose if I assign c1 value 0, c2 equal to some constant 4. Of course, I can assign values by my own choice if boundary conditions are not given. If boundary conditions are given, I need to find c1 and c2 as per my boundary conditions. Suppose if I set c1 equal to 0, c2 equal to 1, this is variable multiple of exponential function. Now, if the roots are complex roots, alpha plus I beta, whenever alpha plus I beta is a root, then it's a complex conjugate also root of the same equation. Then I will get exponential function into c1 cos beta x plus c2 sin beta x. Therefore, in all the three cases, one function is very common, that is exponential function. So therefore, if the solutions are only constant multiples of exponential function, what does it mean is the auxiliary equation have real roots and distinct roots. If the general solution is variable multiple of exponential function, then the equation has real and equal roots. If the solution is a multiple of exponential function along with trigonometric functions sine and cos, then it will be roots are complex roots. Hope you understand all this, right? Now in the next session, we solve classroom workbook questions based on all this. The same procedures you can implement even for third order, fourth order, fifth order, etc. But in the next session, I will discuss few cases if the roots are complex and repeated, right? Thank you so much. This is the end of this particular session.